In the first fraction of a second after the Big Bang, the universe was hot enough that matter and antimatter should have formed in perfect pairs. Physics says those pairs should have erased each other completely, leaving only radiation racing outward at the speed of light, about 186,000 miles per second, or 300,000 kilometers per second. And yet stars formed, atoms endured. We are here is less than #0. 5# is greater than tonight's journey, traces how that survival happened using real measurements, real experiments, and limits written into our best equations. We begin with part 1. Why didn't the universe self-destruct at birth? Where the numbers themselves refuse to cancel out. If matter and antimatter truly emerged in equal numbers, then the earliest universe should have erased itself almost completely, leaving behind only radiation spreading outward, with no stable particles to build anything lasting. The earliest phase we can reconstruct was not a quiet beginning. It was an environment defined by extreme temperature and density, where the distinction between matter and energy barely held. Photons carried enough energy to create particle-antiparticle pairs, and those pairs collided and converted straight back into photons. This was not an occasional interaction. It was the dominant behavior of the universe at that time, governed by the same quantum processes that are tested today in particle laboratories. In that state, nothing favored survival. A proton meeting an antiproton annihilates with near certainty. An electron meeting a positron does the same. The reactions are symmetric, and their probabilities are well measured. If the initial counts were perfectly matched, annihilation would have continued until almost nothing remained except radiation and a small population of particles, like neutrinos, that interact too weakly to disappear completely. Yet that is not the universe we observe. The cosmos today contains atoms, stars, galaxies, and long-lived chemical structures. All of them trace back to a numerical imbalance that existed extremely early, long before the universe became transparent or structured. That imbalance is small enough to sound trivial, but it is measured with enough precision that it cannot be dismissed. The most compact way to express it is through the baryon-to-photon ratio. Cosmological observations show that the number of ordinary matter particles, baryons, mainly protons and neutrons, compared to the number of photons, is about 6 times 10 to the minus 10. In everyday terms, after nearly all matter and antimatter annihilated, roughly 1 extra baryon remained for every 1 to 2 billion photons. This is not a speculative estimate. It is anchored by multiple observations that point to the same value. One comes from the cosmic microwave background, the relic radiation released when the universe was about 380,000 years old. At that time, electrons combined with nuclei, allowing light to travel freely for the first time. The tiny temperature variations in that radiation encode detailed information about the contents of the universe at that moment, including how much ordinary matter was present. The European Space Agency's Planck mission measured those variations across the entire sky with high precision. The pattern of acoustic peaks in the cosmic microwave background depends sensitively on the baryon density. Change the amount of ordinary matter, and the heights and spacing of those peaks shift in a way that cannot be hidden by calibration choices or modeling tricks. When the data are fit, the same small baryon abundance emerges. A second line of evidence comes from a much earlier era Big Bang nucleosynthesis. In the first few minutes, the universe cooled enough for protons and neutrons to bind into light nuclei. The relative amounts of hydrogen, helium, and deuterium produced in that process depend on the baryon density at that time. Astronomical measurements of primordial deuterium in particular act like a sensitive gauge. When those abundances are matched to nuclear reaction rates, measured in laboratories, they again point to a baryon-to-photon ratio in the same narrow range. Two very different epochs, governed by different physics, separated by hundreds of thousands of years, converge on the same number. That convergence is one of the strongest reasons cosmologists treat the matter-antimatter imbalance as a real feature of nature, rather than a modeling artifact. To see why such a small excess matters, it helps to think in terms of process rather than scale. Annihilation in the early universe was extremely efficient. As long as the temperature stayed high, photons continually produced particle-antiparticle pairs, maintaining equilibrium. But expansion steadily lowered the temperature. Eventually, photons no longer carried enough energy to recreate heavy pairs at the same rate. When that happened, creation slowed, while annihilation continued. At that stage, almost every baryon found an anti-baryon partner and disappeared. The outcome was not half the original matter content, it was nearly zero. What remained was the tiny surplus that had no partners left. The efficiency of annihilation is precisely what amplified the importance of that surplus. Without such efficiency, the imbalance would not have mattered. With it, the imbalance became everything. Imagine a ledger with 1 billion matched debits and credits, plus one extra credit. When the accounts are closed, the matched entries cancel. The final balance is defined entirely by the one unmatched entry. In the early universe, annihilation closed the accounts. The leftover baryons set the final balance of matter. That balance was fixed early. By the time the universe reached the stage where nuclei could form, the number of baryons was already determined. Later processes, star formation, galaxy assembly, chemical evolution, did not change the total count. They only rearranged what already existed. This early fixation is why the asymmetry cannot be postponed to later cosmic times. If matter and antimatter had survived in equal numbers until much later, we would expect to see their boundaries today. Large regions of matter and antimatter would annihilate where they met, producing intense gamma-ray emission. Observations from modern gamma-ray telescopes do not show such signals on the required scales. Saoyu Jinghao Lin 5' is greater than. The absence of those signatures supports the conclusion that the imbalance is global and ancient. Historically, the idea that matter and antimatter might exist in separate cosmic domains was taken seriously. In the mid-20th century, when antimatter had only recently been confirmed in laboratories, some models allowed for a symmetric universe divided into vast regions. As observational limits improved, especially with space-based gamma-ray instruments, those models became increasingly constrained. The data favored a universe where antimatter is rare, not because it is hidden, but because it was largely eliminated early. The precision of modern cosmology makes this conclusion unusually robust. The baryon density inferred from the cosmic microwave background is not an isolated parameter. It influences the growth of structure, the formation of galaxies, and the timeline of reionization. Observations from telescopes, including those that probe early galaxies, test the downstream consequences of the same cosmological framework. When those observations align with predictions, they indirectly reinforce the early universe baryon count. What often surprises people is how small the baryonic component is compared to radiation. Photons vastly outnumber baryons, even today. The cosmic microwave background fills space with a dense bath of photons, while baryons form a thin trace by comparison. And yet, that thin trace carries all the familiar structure, stars, planets, and observers. The smallness of the ratio also places strong constraints on theory. Any mechanism that explains the asymmetry must generate an excess of the right order of magnitude. Too little, and there would not be enough matter to form the observed universe. Too much, and the cosmic microwave background and light element abundances would look different from what we measure. The standard model of particle physics allows for small differences between matter and antimatter through known symmetry violations. Those effects are real and measured in experiments involving quarks. However, when they are applied to early universe conditions and followed through quantitatively, they generally do not produce an asymmetry large enough to match the observed baryon-to-photon ratio. That mismatch is not philosophical. It comes from detailed calculations that track reaction rates, thermal histories, and conservation laws. The result is a narrowed target set by observation, and a set of known mechanisms that on their own appear insufficient. We cannot access the first second directly. We cannot reproduce cosmic densities across the observable universe. But we can read the relics left behind. The cosmic's microwave background carries a snapshot of the universe when it first became transparent. Light element abundances preserve a record from the first minutes. Both encode the same asymmetry. This is why the matter-antimatter problem persists as an active area of research. The number is known. The consequences are understood. What remains uncertain is the chain of events that produced that number under early universe conditions. By the time stars ignited and galaxies assembled, the outcome was already decided. Every proton in a star, every nucleus in a planet descends from that early surplus, not because it was large, but because everything else vanished. When such a tiny difference decides whether anything material can exist at all, the focus settles on the earliest moments of the universe. A time when annihilation was still ongoing, equilibrium was beginning to slip, and the balance between matter and antimatter could shift without vanishing entirely. Part 2. If matter meets antimatter, why didn't the early universe erase itself in the first second? If matter and antimatter cancel so efficiently that one encounter can turn mass straight into high-energy light, then the early universe seems like it should have ended as a clean, bright residue of radiation with no stable particles left to build atoms at all. To understand why that did not happen, it helps to picture the early universe the way a careful experimentalist pictures a collider, run not as a scene with empty space, but as a dense medium where the ingredients are decided by temperature, density, and time. In that first second, the universe was hot enough that light itself could repeatedly convert into particle pairs and back again. Photons were not passive messengers. They were active participants trading energy for matter and matter for energy, over and over, in a cycle set by quantum electrodynamics. In a laboratory, we use electromagnetic fields to push particles together and watch the outcomes. In the early universe, there was no apparatus. The density and temperature made the whole cosmos behave like the apparatus. Start with the simplest and most instructive annihilation process, the one involving electrons and positrons. When an electron meets a positron under ordinary conditions, the most common result is 2 photons, each with an energy of 511 kilo-electron-volts, emitted nearly back-to-back to conserve momentum. That specific energy is not an arbitrary number. It is the rest mass energy of an electron written in the units particle physicists use when they count energy directly, is less than #0. 5# is greater than. The 511 kilo-electron-volt line is so characteristic that it became an observational tool in its own right in gamma-ray astronomy, and it is described directly as the hallmark of electron-positron annihilation. Now move that laboratory fact into the first second of cosmic history. At those early temperatures, electron-positron pairs were not rare. They were produced constantly from the photon bath because photons were energetic enough to do the job. At the same time, those pairs annihilated constantly because densities were high and encounters were frequent. This is the key mental adjustment. that makes the self-destruct idea feel less inevitable. Annihilation is not a one-way trap when the temperature is high. It is part of an equilibrium. The environment keeps refilling what annihilation removes, as long as the environment has enough energy per particle. The early universe, however, does not hold conditions steady. It expands. Expansion is not just a geometric detail. Expansion changes the energy budget. As the universe expands, the typical photon energy drops, and the number density of particles falls. At the beginning, equilibrium is strong, because reactions happen faster than the expansion changes the background. But the expansion rate sets a clock that never pauses. At some point, for each species of particle, there is a turnover when interactions can no longer keep up with the expansion. That turnover is where the population stops tracking equilibrium and begins to thin out rapidly. Physicists call this freeze-out, but it is better to imagine it as falling out of step with a moving treadmill. The reactions are still there, but the environment is changing faster than the reactions can correct the inventory. For electrons and positrons, the turning point arrives when the typical photon energy drops below what is needed to create fresh pairs efficiently. Once that happens, pair creation becomes suppressed, while annihilation keeps going. The result is an enormous reduction in positron abundance. Positrons do not run out of reactions. They run out of the conditions that keep them continuously replenished. Annihilation becomes one-sided because creation can no longer keep the balance. This alone begins to answer the first-second paradox. The early universe did not fail to annihilate. It annihilated extremely well. What changed is that the universe stopped remaking what it annihilated. In other words, the process that looks like a perfect cleanup is only perfect at removing pairs. It does not remove an imbalance. If the universe contains even a slight surplus of one sign of charge compared to the other, annihilation will remove the matched pairs and leave the surplus behind. That surplus is not optional. It is forced by later facts. The universe contains protons, and long after positrons vanished, it contains electrons to balance charge. The electron surplus is effectively tied to the proton surplus, because a universe with net charge would behave very differently and is not supported by observation. So electron-positron annihilation is not a side story. It is a concrete demonstration of how the universe can shed almost an entire population of antiparticles while still retaining the charged particles needed for atoms later. Now, scale up to baryons, the family that includes protons and neutrons. Proton-antiproton annihilation is even more violent in its outcomes because baryons are heavier and their annihilation cascades into showers of lighter particles, including pions and gamma rays. In the earliest universe, baryon-antibaryon pairs could be created when the temperature was high enough. But as expansion cooled, the plasma-baryon pair creation became inefficient in the same broad sense as it did for electrons and positrons, only earlier and at higher energies. When that threshold was crossed, annihilation drove the baryon and antibaryon populations down until almost none remained, and the leftover was set by whatever imbalance existed before equilibrium broke. This is where the phrase perfect cleanup becomes the wrong expectation. Perfect cleanup of pairs is exactly what leaves a remnant when the starting counts are not identical. If there is one extra survivor per enormous number of pairs, the cleanup makes that survivor dominate the final accounting. The early universe behaves like an accounting system that cancels matched entries with ruthless efficiency. Matched entries vanish. Unmatched entries define what is left. You might wonder whether such a remnant could be created late after the first second, perhaps, by astrophysical processes. The sky places strong limits on that. If large amounts of antimatter survived into a later era and mixed with matter, the boundaries would produce intense gamma radiation from ongoing annihilation. Modern gamma-ray observations do not show the signatures expected from matter-antimatter domain boundaries on cosmic scales. The most natural interpretation is that the imbalance was established early and applied globally, not as a patchwork of separated regions. There is another observational clue that makes the timing feel more concrete. The cosmic microwave background is a relic of the era when the universe became transparent hundreds of thousands of years after the Big Bang. NASA describes this transition, called recombination, as the time when electrons combined with nuclei so that light could travel freely, clearing the earlier scattering fog, is less than #0. 5# is greater than mat. Relic radiation retains a precise imprint of how much ordinary matter existed by then, because ordinary matter changes the behavior of the photon-baryon fluid that carried sound waves through the plasma. Planck's final results measure the baryon density parameter with sub% precision, tying down the amount of ordinary matter present, with little room for improvisation. That matters because it tells you the remnant survived long before recombination. The universe did not recover from annihilation later. The surviving matter had to be present early enough to influence the plasma physics that Planck measured. Is less than #0. 5# is greater than. In parallel, Big Bang, nucleosynthesis occurring in the first minutes, depends on the same baryon inventory to produce the observed light. Element abundances and studies of nucleosynthesis and deuterium constraints point to a first baryon to photon ratio in the same order of magnitude around 6 × 10⁻⁻10. So the early universe logic forms a tight chain. High temperature sustains equilibrium. Equilibrium keeps making pairs. Expansion cools. The plasma cooling suppresses creation. Annihilation removes pairs, and a small imbalance becomes the leftover inventory. The later universe, measured through the cosmic microwave background and primordial element abundances, confirms that leftover inventory existed and stayed. This chain does not require exotic assumptions to explain why annihilation did not eliminate absolutely everything. It requires only the standard interplay between reaction rates and expansion. The deeper tension, and the reason the topic stays active in research, is that this chain also exposes what annihilation cannot do. Annihilation can magnify an imbalance into dominance, but it cannot create the imbalance by itself. If the counts start perfectly, equal annihilation plus expansion leaves a universe that is overwhelmingly radiation with vanishing baryonic matter. That is why the first-second paradox is not really about whether annihilation is strong enough. It is about why the initial counts were not exactly symmetric. There are several places one might try to hide such an asymmetry, and most of them fail quickly when held against data. One might try to push antimatter far away, but domain boundaries should light up in gamma rays. One might try to claim the imbalance arises from late astrophysical processes, but the cosmic microwave background and nucleosynthesis lock the baryon inventory in place far earlier than stars, is less than #0. 5# is greater than. One might try to treat the imbalance as measurement error, but independent methods converge. The remaining space for explanations sits in early-time particle physics, where tiny symmetry violations can, under the right conditions, bias outcomes by 1 part in a billion, without producing glaring macroscopic leftovers. Even electron-positron annihilation contains a lesson that is easy to miss if you focus only on drama. The 511 kilo electron-volt photons are a receipt of a conversion. In the early universe, the receipts were everywhere, but they did not accumulate into a record we can read directly today because the universe kept scattering and rethermalizing radiation until much later. What we can read is the downstream bookkeeping, the way the surviving matter shaped the acoustic pattern in the microwave background, and the way it set the nuclear reaction pathway that determined deuterium and helium. Those are indirect records, but they are quantitative and mutually consistent. A practical example helps keep the mechanism grounded. Consider a crowd exiting a stadium through two kinds of gates. One kind of gate opens both ways, so people can enter and leave, keeping numbers balanced inside. The other kind of gate becomes one way, when security rules change, so people can only leave, not re-enter. In the earliest universe, high temperature kept the gates two-way for many particle species because creation and annihilation balanced. Expansion changed the rules. The gates became effectively one way for pair creation, once the average photon energy fell, and then annihilation depleted the pairs. If there was a slight bias in the head count, the final stadium is not empty. It contains the bias. This is also why the first-second framing is both right and misleading. Right because much of the relevant freeze-out behavior occurs extremely early. Misleading because no single timestamp does all the work. Different species fall out of equilibrium at different times, and the universe passes through a ladder of thresholds. The overall outcome is still simple. Once the universe cools past the relevant threshold's antimatter in bulk does not survive, and the surviving matter is the small excess. The early universe erasure looks less like a failure and more like a mechanism with a clear limitation. It removes pairs efficiently, it preserves a bias, and it locks in the final inventory once expansion makes pair creation ineffective. The sky confirms the locked-in inventory through microwave background structure and light element abundances. That leaves a sharper pressure point that cannot be handled by annihilation physics alone, and it lands on direct evidence, not interpretation, because the next step depends on whether antimatter was ever more than a mathematical mirror in our equations, which is exactly where Part 3, what did we actually measure that proves antimatter is real, not a math trick, begins. Before antimatter became a word we use comfortably, before it appeared in textbooks or documentaries, it existed only as an uncomfortable implication of mathematics, and many physicists hoped it would quietly go away. In the late 1920s, the equations describing electrons and relativity refused to behave politely. Paul Dirac had written down a theory that merged quantum mechanics with special relativity, and the result was powerful, precise, and troubling. The equations predicted electrons exactly as experiments already knew them, but they also predicted something else, something with the same mass as the electron and the opposite electric charge. At first, this was not celebrated. It was treated as an embarrassment, a surplus solution that needed interpretation or removal. At the time, physics was already crowded with particles. Adding a mirror version of every known particle felt extravagant. Dirac himself tried to interpret the unwanted solutions as electrons hidden in a background sea of negative energy states. It was an elegant idea, but even he understood that elegance was not evidence. What mattered was whether nature actually built such objects. If a positively charged electron existed, it had a precise mass, a precise charge, and a precise way it should move in electric and magnetic fields. If it did not exist, the equations would remain clever abstractions with no physical anchor. The turning point came not from a grand laboratory built to test antimatter, but from a modest device already sitting on a tabletop, quietly recording traces left by particles from space. That device was the cloud chamber. It worked on a simple principle. When a charged particle moves through a supersaturated vapor, it leaves behind a visible trail of droplets along its path. Those trails curve in magnetic fields, and the direction of curvature reveals the sign of the particle's charge. By the early 1930s, cloud chambers had become trusted tools. They were used to study cosmic rays, high-energy particles arriving from space that constantly bombard Earth. Cosmic rays were not yet well understood, but they were energetic enough to produce unusual events. Researchers photographed thousands of tracks, most of them familiar. Occasionally, something did not fit. In August of 1932, Carl Anderson was studying photographs from his cloud chamber at the California Institute of Technology. The chamber sat inside a magnetic field, and Anderson had placed a lead plate across its middle. The plate forced particles passing through to lose energy, making it possible to compare the curvature above and below the plate. This detail mattered. It allowed Anderson to estimate both the charge and the momentum of the particle. On one photograph, Anderson noticed a track that curved the wrong way. It bent as if the particle carried a positive charge, but its curvature corresponded to a mass far too small to be a proton. Protons were known, and they curved much less, under the same conditions. This track behaved like an electron in every respect except one. Its charge was reversed. This was not a single, ambiguous event. Anderson carefully analyzed the geometry, the energy loss, and the curvature radius. The numbers lined up. The particle had the same mass as an electron and the opposite charge. There was no room to reinterpret it as a known particle misbehaving. In his paper, Anderson described it cautiously, but the implication was clear. A positively charged electron existed. The positron was not a trick of algebra. It was a mark on photographic film. The importance of that moment is easy to underestimate with hindsight. Physics is full of predictions that later become measurements. But in 1932, this was different. Antimatter was not expected in the sense that neutrons or neutrinos were expected. It emerged from equations that many hoped would simplify away. Instead, nature answered directly. The discovery mattered not just because it confirmed a particle, but because it changed the rules of credibility. Once one antiparticle was real, the door opened to others. The logic that had seemed excessive became economical. If electrons had antiparticles, there was no longer a strong reason to believe protons or other particles would not. Soon after, laboratory experiments began to reproduce positrons in controlled settings. High-energy photons striking matter were observed to produce electron-positron pairs, exactly as quantum electrodynamics predicted. These processes were no longer cosmic curiosities. They could be triggered, measured, and repeated. Annihilation events produced gamma rays with characteristic energies, and those energies matched the rest mass energy of electrons. Each observation reinforced the same conclusion. Matter and antimatter were symmetric partners in nature's accounting. The cloud chamber photograph became one of the most famous images in physics, not because it was beautiful, but because it was definitive. It tied an abstract prediction to a measurable phenomenon. That connection is what allows antimatter to play a role in cosmology at all. Without it, discussions of matter-antimatter imbalance would rest on speculation. As experimental techniques improved, antimatter became routine rather than exotic. Particle accelerators produced antiparticles in abundance. Detectors tracked their paths, measured their lifetimes, and studied their interactions. Antiprotons were discovered. Antineutrons followed. Each discovery extended the symmetry. At this stage, the question shifted again. If antimatter is real and produced naturally in high-energy environments, then the early universe with its extreme energies should have been filled with it. That conclusion does not come from philosophy. It comes from scaling up laboratory results. If accelerators can produce particle-antiparticle pairs at high energy, a universe with far higher energy density should do the same everywhere. Annihilation in the early universe only makes sense if there was something to annihilate. The laboratory confirmation of antimatter removes any ambiguity. The early universe did not almost contain antimatter. It did contain antimatter. The same processes that produce positrons in detectors would have produced them naturally in the hot plasma after the Big Bang. There is another subtlety here that deepens the story. Anderson's positron was discovered using cosmic rays, not a human-built accelerator. Cosmic rays are particles accelerated by astrophysical processes, likely involving supernova remnants and magnetic fields in our galaxy. The fact that antimatter appears in cosmic rays means it is not confined to artificial environments. Nature itself produces it whenever energies are high enough. This matters for cosmology because it shows that antimatter production is not rare or contrived. It is a generic consequence of energy being converted into mass according to well-tested rules. Once that principle is accepted, the presence of antimatter in the early universe becomes unavoidable. Over time, detection methods evolved. Cloud chambers gave way to bubble chambers, then to wire chambers and silicon detectors. Each new generation increased precision and statistics, but the basic signatures remained the same: charge sign, curvature in magnetic fields, energy loss, annihilation products. The evidence accumulated not in one dramatic leap, but in thousands of consistent measurements. By the mid-20th century, antimatter had moved from novelty to infrastructure. Experiments at particle laboratories routinely included antiparticles in their analyses. The language of particle physics absorbed them naturally. There was no longer a serious question about their existence. The remaining questions were about their properties and their role in larger systems. This experimental certainty is what allows cosmologists to frame the matter-antimatter problem sharply. If antimatter were a bookkeeping device, one could imagine adjusting the mathematics to remove it. But once it is observed, tracked, and manipulated, it becomes part of the inventory of the universe. The imbalance problem becomes unavoidable. The historical arc from Dirac's equation to Anderson's photograph also illustrates a broader pattern in science. Equations can suggest possibilities, but experiments decide which possibilities nature uses. In this case, nature chose to include antimatter. That choice forces us to confront its consequences on the largest scales. It also explains why later cosmological measurements are taken so seriously. When the cosmic microwave background and light element abundances indicate a universe dominated by matter, the conclusion rests on the assumption that antimatter would behave as experiments say it does. Because those experiments are solid, the cosmological inference is solid as well. There is no need to imagine exotic forms of antimatter hiding in unknown states to reconcile the data. Ordinary antimatter with ordinary interactions would leave observable traces if it were present in large amounts today. Those traces are not seen. The simplest reading is that antimatter existed early and was removed efficiently, leaving the small excess discussed earlier. Carl Anderson's cloud chamber track thus carries a weight far beyond its size. It anchors a chain of reasoning that runs from laboratory benches to the first second of cosmic history. Without that track, the antimatter problem would dissolve into ambiguity. With it, the problem sharpens into a precise scientific question. Once antimatter is recognized as a measured part of nature, it is no longer enough to simply note that it exists. Attention turns to a deeper imbalance. Why, in a universe that produces antimatter with ease, matter ultimately retained the advantage? That focus brings us to the point where known laws are examined on their own terms to see whether they can account for this outcome without modification, and where the limits of current theories begin to appear. Part Cat. Why doesn't the standard model automatically create the imbalance we need? If the laws of physics already allow matter and antimatter to behave differently, then the universe should not have needed any extra help to end up matter-dominated. At first glance, the standard model of particle physics seems to provide exactly what the early universe required. It allows violations of a symmetry known as CP. the combined symmetry of charge and parity. Charge distinguishes matter from antimatter. Parity distinguishes left from right. When CP symmetry holds perfectly, the behavior of matter and antimatter is mirror-balanced. When it is violated, that balance is broken, at least slightly, is less than #0. 5# is greater than. And the Standard Model does contain CP violation not as an afterthought, but as a measured and indispensable part of how quarks behave. This realization emerged gradually. In the 1960s, experiments studying neutral kaons revealed that nature does not treat matter and antimatter as exact opposites. Certain decays occurred more often than their mirror processes. The discovery was small in magnitude but unambiguous in implication. CP symmetry was not absolute. The universe had written a preference into its rules. Later, this preference was woven into the structure of the Standard Model through what is now known as the Kobayashi-Maskawa mechanism. The idea is subtle but concrete. Quarks come in multiple types, and when they change type through weak interactions, the probabilities depend on a mixing pattern that includes a built-in asymmetry. That asymmetry appears as a phase in the mixing matrix, and its effects have been measured in laboratories around the world, is less than #0. 5# is greater than experiments at facilities such as the Stanford Linear Accelerator Center KEK in Japan and CERN in Europe have mapped these effects with high precision. There is no doubt that CP violation exists in the Standard Model. Given this, the natural expectation is simple. If CP violation is real and measured, and if the early universe was filled with quarks undergoing rapid interactions, then a matter-antimatter imbalance should emerge automatically. That expectation feels reasonable until the numbers are examined carefully. This is where the Standard Model begins to struggle. The amount of CP violation it contains is not a free parameter. It is fixed by experiments. When theorists take those measured values and apply them to realistic conditions in the early universe, the resulting imbalance is extraordinarily small. Not small in a casual sense, but small by many orders of magnitude compared to what observations demand. The observed baryon asymmetry corresponds to roughly 1 extra baryon for every 1 to 2 billion photons. The CP violation generated by the Standard Model, when folded through known reaction rates and thermal histories, typically produces an imbalance far below that level. In many careful analyses, the predicted asymmetry is smaller by factors of 10,000 or more. This mismatch does not arise from sloppy estimates. It comes from detailed calculations that track how CP-violating processes compete with other effects in the hot plasma. One of the most important of those effects is equilibrium. The early universe was extremely efficient at erasing asymmetries unless specific conditions were met. For an asymmetry to survive, it must be generated out of equilibrium. If reactions occur fast enough to maintain equilibrium, any small bias is quickly washed out. The Standard Model contains CP violation, but it also contains interactions that restore balance with remarkable efficiency. The result is that CP violating effects exist, but they are diluted before they can leave a lasting imprint. To see this more clearly, consider the environment near the electroweak scale, when the Higgs field settled into its present form and particles acquired mass. This transition reshaped the particle landscape. It is tempting to imagine that such a dramatic change would naturally lock in a matter excess. Many researchers explored this possibility under the name electroweak baryogenesis. The idea is appealing. The electroweak transition involves expanding regions of broken symmetry, where particles experience changing conditions. CP-violating interactions at the boundaries of these regions could in principle bias reactions in favor of matter. But when the Standard Model parameters are used, the transition is too smooth and the CP violation too feeble. The bias never grows large enough. This conclusion did not emerge overnight. It took years of work combining particle physics, finite temperature field theory, and cosmology. The calculations were difficult and sometimes controversial, but as techniques improved and independent groups checked each other's results, a consensus formed. The Standard Model as it stands does not naturally generate the observed baryon asymmetry under realistic early universe conditions. What makes this result particularly striking is that it is not a failure of measurement. The Standard Model is one of the most successful theories ever constructed. Its predictions have been confirmed across a vast range of experiments. The discovery of the Higgs boson at the Large Hadron Collider in 2012 completed its particle roster exactly as anticipated. Yet this same theory, so effective at describing laboratory phenomena, appears insufficient when asked to explain a cosmic fact written across the sky. There is a historical echo here. In the early 20th century, classical physics explained many observations with impressive accuracy, yet failed to account for blackbody radiation and atomic stability. Those failures did not invalidate classical physics. They marked its limits. In a similar way, the baryon asymmetry highlights a boundary of the Standard Model's explanatory power. Another way to appreciate the problem is to focus on scales. CP violation in the Standard Model is most prominent in processes involving heavier quarks. In the early universe, those quarks were present only briefly before decaying into lighter ones. Their CP violating effects were real but fleeting. Meanwhile, the reactions that could erase asymmetries operated continuously and efficiently. The imbalance simply did not have time to accumulate. This imbalance of timescales is central. Creating a matter excess requires more than a preference. It requires persistence. The Standard Model provides preference without persistence. The early universe demands both. Experiments reinforce this picture. Measurements of CP violation in meson decays are exquisitely precise. They agree with Standard Model predictions to remarkable accuracy. There is little room to increase CP violation within the known framework without conflicting with laboratory data. This means the weakness of baryogenesis in the Standard Model is not something that can be adjusted away. It is built in. The situation becomes even tighter when additional constraints are considered. Any new source of CP violation large enough to generate the cosmic asymmetry must also avoid producing signals that experiments have not seen, such as permanent electric dipole moments of particles. Searches for these effects are extraordinarily sensitive. Their null results restrict how much CP violation can exist at low energies. The Standard Model sits comfortably within these bounds. Many hypothetical extensions do not. This interplay between cosmology and precision experiments is one of the most instructive aspects of the problem. A question that begins with the survival of matter in the early universe feeds directly into measurements performed on tabletop apparatuses and particle beams. The cosmos and the laboratory constrain each other. It is also why the phrase new physics appears so often in discussions of baryogenesis. The phrase does not mean abandoning what works. It means adding ingredients that respect existing measurements while changing early universe behavior in a targeted way. Additional fields, new interactions, or altered phase transitions are all possibilities explored in the literature. What remains clear is that the Standard Model alone does not close the accounting. It explains how particles interact today with extraordinary precision. It does not by itself explain why there is more matter than antimatter in the universe. That gap is not a philosophical discomfort. It is a quantitative mismatch between prediction and observation. This mismatch sharpens the narrative developed in the earlier parts. Antimatter is real and well measured. Annihilation is efficient and understood. The surviving imbalance is small and precisely quantified. When the known laws are applied carefully, they do not naturally produce that imbalance. The problem is not vague. it is narrowly defined. In science, such problems are valuable. They tell us where to look next. They point to regimes where familiar principles may need reinforcement from new ones. In this case, the early universe becomes a testing ground for ideas that extend beyond the standard model, while remaining anchored to experimental reality. Once the standard model is shown to be insufficient in this precise numerical way, attention turns to the exact conditions required for an imbalance to survive at all. Those conditions were first clearly formulated in the 1960s, defining what must occur for matter to emerge with a lasting advantage. Part 5. What are Sakharov's 3 conditions? And why do they sound like a recipe for existence? If the universe began with no preference at all, then no amount of time, no amount of expansion, and no amount of annihilation could have produced the imbalance we measure today, unless certain rules were quietly violated very early on. By the mid-1960s, this had become an unavoidable conclusion. Physicists had learned that antimatter was real, that annihilation was efficient, and that the surviving excess of matter was extremely small, yet decisive. What remained unclear was not the size of the imbalance, but the logic that could allow it to appear and persist without being erased. In 1967, Andrei Sakharov approached the problem with an unusual kind of clarity. Instead of proposing a detailed mechanism, he asked a more basic question. Under what conditions could any mechanism work at all? Sakharov's answer was not expressed as speculation. It was framed as a set of necessary requirements. If even one of them were missing, the universe would inevitably slide back toward perfect symmetry. These requirements are now known as Sakharov's conditions, and they have guided every serious attempt to explain baryogenesis ever since. The first condition concerns baryon number. Baryons are particles like protons and neutrons, and baryon number is a bookkeeping quantity that counts how many of them exist minus how many antibaryons exist. In everyday particle interactions, baryon number appears to be conserved. Protons may scatter, combine, or rearrange, but the total count does not change. If this conservation were absolute, the universe would be trapped. Starting from 0 net baryon number, it would remain 0 forever. Sakharov recognized that this could not be the case if the universe ended up with an excess of baryons. Somewhere, at some time, processes must exist that change baryon number. Not rearrange it, not hide it, but genuinely violate it. This idea was bold at the time. It challenged the intuition built from laboratory experiments where baryon number seemed untouchable. But Sakharov's reasoning was simple. If you cannot change the count, you cannot create a surplus. Later developments in particle physics showed that this intuition was incomplete. In the standard model, baryon number is not an exact symmetry at high energies. Certain non-perturbative processes can violate baryon number under extreme conditions. These processes are negligible today, but in the hot early universe they become relevant. This did not solve the problem by itself, but it established that the first condition was not forbidden by known physics. The second condition addresses symmetry between matter and antimatter more directly. Sakharov noted that even if baryon number violation exists, it is useless without a preference. If processes create baryons and antibaryons at the same rate, the net result is still 0. To bias the outcome, nature must treat matter and antimatter differently. This requires violation of charge conjugation symmetry and the combined symmetry of charge and parity, known as CP. By the time Sakharov wrote his paper, hints of CP violation were already emerging. In 1964, experiments studying neutral kaons showed that certain decays favored matter slightly over antimatter. The effect was tiny, but it was real. CP symmetry was not exact. This discovery provided crucial support for Sakharov's second condition. Nature did contain a built-in asymmetry, however small. Yet Sakharov understood something that later work made explicit. CP violation alone is not enough. A small bias does nothing if it is constantly cancelled by other processes. The universe needs a way to protect that bias long enough for it to matter. This brings us to the third condition departure from thermal equilibrium. In equilibrium, every reaction is balanced by its reverse. Any small excess, created by a CP-violating process, is rapidly erased by the opposite reaction. Equilibrium is relentless. It smooths out differences with extraordinary efficiency. The early universe, however, was not static. It was expanding and cooling. Expansion drives systems out of equilibrium by changing conditions faster than reactions can respond. Sakharov recognized that this cosmic evolution could provide the necessary imbalance. If baryon number violation and CP violation operate while the universe is out of equilibrium, then a net baryon excess can survive. Each of these conditions addresses a different failure mode. Without baryon number violation, nothing changes. Without CP violation, changes cancel. Without departure from equilibrium, changes are undone. Only when all three are present at the same time does the door open. What makes Sakharov's insight powerful is that it does not depend on the details of a particular model. It applies to any attempt to explain the matter-antimatter imbalance, whether based on known physics or on proposed extensions. It acts as a filter. Many ideas fail immediately because they violate one of the conditions. Historical context helps here. Sakharov was not working in isolation. The 1960s were a period of rapid growth in both particle physics and cosmology. The Big Bang model was becoming dominant. The cosmic microwave background had just been discovered. Questions about the early universe were no longer philosophical. They were becoming quantitative. Sakharov's paper fit perfectly into this shift. It transformed a vague puzzle into a structured problem. Later researchers tested the conditions against specific scenarios. Electroweak baryogenesis explored whether the electroweak transition could provide the required out-of-equilibrium environment. Grand unified theories examined whether heavy particle decays could violate baryon number strongly enough. Leptogenesis investigated whether an asymmetry in leptons could be converted into a baryon asymmetry. Each approach can be evaluated by checking how it satisfies Sakharov's requirements. The clarity of this framework is why the conditions sometimes sound like a recipe, not because they guarantee success, but because they define what success demands. A recipe does not cook the meal by itself. It tells you what ingredients must be present. Sakharov's conditions tell you what ingredients the universe must have used regardless of the specific cooking method. One instructive example comes from attempts that focus only on CP violation. It is tempting to imagine that increasing CP violation slightly would solve the problem, but without baryon number violation, no amount of bias helps. The universe would still conserve baryon number exactly, and the final count would remain 0. Similarly, models that allow baryon number violation but operate in equilibrium fail quietly. They generate asymmetries that vanish almost as soon as they appear. This logic explains why the standard model discussed in the previous part falls short. It contains CP violation and even baryon number violation under certain conditions, but it struggles to provide the necessary departure from equilibrium with sufficient strength. The electroweak transition, as currently understood, is too smooth. The required imbalance never becomes protected. What Sakharov offered was not a solution, but a map. That map has held up remarkably well. Decades of experimental progress have not invalidated any of the three conditions. Instead, they have sharpened their meaning. Precision measurements constrain how much CP violation can exist. Searches for proton decay test baryon number violation. Cosmological observations constrain when and how equilibrium was broken. This interplay between theory and measurement gives the conditions a practical role. They are not historical curiosities. They actively shape experimental programs. For example, experiments searching for electric dipole moments probe new sources of CP violation. Their sensitivity reaches levels that can rule out entire classes of baryogenesis models. Is less than #0. 5 is greater than. In the same way, collider experiments test whether new particles could create the necessary out-of-equilibrium conditions in the early universe. There is also a deeper reason Sakharov's conditions remain central. They separate what is logically necessary from what is merely convenient. Many mechanisms can be imagined. Very few satisfy all three constraints without conflicting with data. The conditions keep speculation anchored to reality. It is worth noting that Sakharov's original paper was concise. It did not contain pages of calculation. Its power lay in its structure. By isolating the minimal requirements, it allowed later generations to explore details without losing sight of fundamentals. That is a rare achievement in theoretical physics. As cosmological data improved, especially with missions measuring the cosmic microwave background, the target became sharper. The baryon asymmetry is no longer loosely estimated. It is quantified with high precision. That precision feeds back into Sakharov's framework, narrowing the range of viable scenarios. Today, every serious discussion of the matter-antimatter imbalance begins implicitly or explicitly with Sakharov's three conditions. They are not optional assumptions. They are logical consequences of the problem itself. The universe either satisfied them or it would not look the way it does. What remains open is how nature implemented them. The conditions do not tell us which particles were involved, how strong the violations were, or at what exact temperatures they operated. Those details are where modern research focuses. These requirements did not remain confined to theory for long. Decades before they were used to frame cosmological models, particle experiments were already revealing subtle violations of symmetry in decay processes. Those early results offered the first tangible signs that the necessary conditions for an imbalance were physically real, not merely mathematical expectations. Part 6. How did a forbidden kaon decay in 1964 change cosmology forever? What if the first clear sign that matter and antimatter are not treated equally by nature was not written in the sky, but traced quietly inside a laboratory beamline particle by particle? By the early 1960s, physicists already knew that antimatter existed and that annihilation was efficient. What they did not yet know was whether the laws of physics themselves contained any built-in preference, however small, between matter and antimatter. Symmetry was still the default expectation. If a process occurred for matter, its mirror should occur for antimatter with exactly the same probability. This assumption was not philosophical. It was grounded in decades of experiments that had failed to reveal any asymmetry. The stage where that assumption would finally be tested was unexpectedly modest. At Brookhaven National Laboratory, beams of neutral kaons were being produced and studied. Kaons are unstable particles containing a strange quark paired with a down antiquark, or the opposite combination. Neutral kaons are particularly subtle because they are not fixed objects. They oscillate between two related states as they travel a quantum behavior that makes them unusually sensitive probes of symmetry. In simple terms, neutral kaons come in two main varieties, distinguished by how they decay. One decays quickly into 2 pions, the other more slowly into 3 pions. According to the prevailing understanding, these decay patterns were linked directly to CP symmetry. If CP symmetry were exact, each kaon state would have a strictly defined decay channel. Certain decays were effectively forbidden. James Cronin and Val Fitch were not hunting for a cosmic imbalance. They were testing the structure of weak interactions with great care. Their experiment sent a beam of neutral kaons through a detector system designed to identify decay products precisely. Most events behaved exactly as expected. Then a small number did not. A kaon that should have decayed only into 3 pions occasionally decayed into 2. The probability was tiny, about 2 events in 1,000, but it was unmistakable. The decay products were clear, the statistics robust, and the result persistent. This was not noise. It was a violation of CP symmetry. The importance of this observation lay not in its size, but in its existence. For the first time, matter and antimatter were shown to behave differently under the weak interaction. The difference was subtle, but it was real. In 1964, that single result rewrote a foundational assumption. Nature did not enforce perfect symmetry. The reaction within the physics community was cautious. Extraordinary claims demand extraordinary care, and Cronin and Fitch provided it. Independent checks confirmed the effect. The interpretation matured. CP violation was no longer a theoretical curiosity. It was a measured property of the universe. The connection to cosmology was not immediate, but it was inevitable. If matter and antimatter behave differently in even one class of processes, then the early universe had access to a tool that could bias outcomes. Sakharov's second condition was no longer hypothetical. It had experimental support. At the same time, the kaon result carried a warning. The asymmetry was extremely small. 2 decays in 1,000 were enough to overturn a symmetry principle, but far too small by themselves to explain the cosmic baryon asymmetry. This dual message shaped decades of thinking. CP violation existed, but it was delicate. To appreciate how delicate it helps to look at the scale, the baryon asymmetry of the universe corresponds to roughly 1 extra baryon per 1 to 2 billion photons. Any microscopic bias responsible for that outcome must survive enormous dilution and competition from equilibrium processes. The kaon asymmetry, while groundbreaking, appeared too weak to shoulder that burden alone. Still, the discovery changed what physicists considered possible. Before 1964, many discussions of baryogenesis were speculative because the required asymmetry had no experimental anchor. After Cronin and Fitch, that anchor existed. The universe was permitted, by its own rules, to distinguish matter from antimatter. The historical context adds weight to this shift. In 1980, James Cronin and Val Fitch were awarded the Nobel Prize in Physics for the discovery of CP violation. The Nobel citation emphasized the fundamental nature of the finding, not its immediate applications. Yet by then, cosmologists had already absorbed its implications. A door that had been closed was now open, even if only a crack. The kaon system also revealed something deeper about how asymmetry works. CP violation does not appear as a blunt preference. It emerges through interference between different quantum pathways. In neutral kaons, 2 possible decay routes overlap, and their interference produces a slight imbalance. This means CP violation is inherently sensitive to phase relationships, lifetimes, and mixing. It is not something that can be dialed up arbitrarily. That insight carried forward into the development of the Standard Model. When Makoto Kobayashi and Toshihide Masukawa extended the quark mixing framework to include additional quark families, they showed how CP violation could arise naturally from the structure of the theory. Their work, inspired in part by the kaon results, provided a coherent explanation for observed asymmetries. Yet, even as the theoretical framework matured, the cosmological challenge remained. When the measured CP violation from kaons and later from other meson systems was inserted into early universe calculations, the numbers did not grow large enough. The asymmetry was real, but it was too small. The kaon discovery proved that symmetry could be broken, but it also demonstrated how gently nature chose to do so. This tension sharpened the research program. If CP violation existed but was insufficient, then either additional sources existed at higher energies, or early universe conditions amplified small effects in ways not yet understood. Both possibilities became active areas of investigation. The kaon experiment also illustrates an important methodological point. The universe often reveals its deepest properties, not through dramatic events, but through rare deviations that persist under scrutiny. A decay channel suppressed to the level of a few tenths of a percent was enough to reshape our understanding of symmetry. That lesson carries directly into cosmology. The matter-antimatter imbalance is not large, it is a trace, yet that trace defines the entire visible universe. The kaon decay taught physicists to take small asymmetries seriously, because their consequences can be enormous when amplified by cosmic history. Another often overlooked aspect is the experimental environment itself. The kaon beam was not designed to answer cosmological questions. It was built to probe the weak interaction. The cosmological significance emerged only after the fact. This is a recurring pattern in science. Fundamental discoveries often arise as byproducts of careful measurement rather than targeted searches. As more CP-violating systems were studied, including B mesons, in later decades the picture became clearer but not simpler. CP violation was confirmed as a general feature of weak interactions, yet always small. Each new measurement reinforced the same conclusion reached with kaons. The asymmetry exists, but it is finely constrained. For cosmology, this meant that any successful explanation of baryogenesis had to respect these laboratory results. One could not simply assume a large CP-violating effect without consequences. Precision experiments had already set boundaries. The early universe had to work within them, or introduce new physics that hid its effects from low-energy tests. The kaon decay thus occupies a unique place in the story. It is both the first confirmation that matter and antimatter are not treated identically, and the first indication that the difference might be too subtle to solve the cosmic problem by itself. It provided permission and constraint at the same time. Looking back, it is striking how much hinged on those few anomalous decays. Without them, discussions of baryogenesis would lack empirical footing. With them, the problem became sharply defined. The universe allows asymmetry, but only under tight rules. The measured CP violation is real, but its magnitude falls short of what the universe requires. That shortfall directs the search toward earlier cosmic conditions, when temperatures were higher, symmetries were less rigid, and fields could undergo rapid transitions. In that environment, asymmetries might have grown far beyond what kaon decays alone can produce. One such moment occurs during the electroweak era, when the vacuum itself reorganized and imposed new constraints on how matter could survive. Part 7. Did the electroweak phase transition fail us? Or is it pointing to new particles? If the Higgs field reshaped the universe and decided which particles could have mass, then it seems natural to ask why that same moment did not also lock in a large excess of matter over antimatter. To see why this question sits at the center of modern baryogenesis research, it helps to return to what the electroweak era actually represents. Very early in cosmic history, when temperatures were far higher than anything reached today, the electromagnetic force and the weak nuclear force were not distinct. They were unified into a single interaction. Particles did not yet possess the masses we now take for granted. Electrons, quarks, and even the carriers of the weak force behaved as if mass were not part of the rules. This changed as the universe expanded and cooled. At a temperature of roughly 100 billion degrees Kelvin, the Higgs field settled into a new configuration. Its value throughout space became non-zero, and particles interacting with it acquired mass. This event is known as the electroweak phase transition. It was not a small adjustment. It redefined how particles moved, decayed, and interacted. From the perspective of baryogenesis, the electroweak transition looks promising. It involves a rapid change in the state of the vacuum. It happens at energies where known CP violation operates. It takes place during a period when baryon number violating processes allowed by the standard model at high temperature can occur. All three of Sakharov's conditions appear to be within reach. For many years, this combination motivated a large body of work under the name electroweak baryogenesis. The core idea is straightforward. If the electroweak transition was sufficiently violent, it could drive the universe far from thermal equilibrium. Expanding regions of the new Higgs phase would form boundaries, often described as bubble walls. Particles interacting with these walls could experience CP-violating effects that bias reactions in favor of matter. The picture is attractive because it ties the cosmic asymmetry directly to physics, that is, at least in principle, testable in laboratories. Unlike scenarios that rely on extremely high energies far beyond current experiments, electroweak baryogenesis operates near scales explored by particle colliders. If it works, it suggests that the origin of matter is encoded in physics we can probe. However, the strength of this idea depends critically on the nature of the electroweak transition itself. Phase transitions come in different types. Some are abrupt, proceeding through the nucleation and growth of bubbles. Others are smooth, with no sharp separation between phases. Only the first type provides the strong departure from equilibrium needed to protect a growing asymmetry. Here, the standard model delivers an unwelcome answer. Detailed studies of the Higgs potential, informed by the measured Higgs boson mass of about 125 giga-electron volts, show that the electroweak transition in the standard model is not a violent first-order transition. It is a smooth crossover. There are no expanding bubble walls. There is no sharp front where equilibrium is dramatically broken. This result is not speculative. It follows from finite temperature calculations that use the same Higgs parameters measured at the Large Hadron Collider. When those parameters are inserted, the mathematics points consistently toward a smooth transition. The universe changed its state but gently, in a way that left equilibrium largely intact. This gentleness matters. In a smooth crossover, any CP-violating bias that appears is rapidly neutralized by inverse processes. The system never strays far enough from balance for a net baryon excess to freeze in. The electroweak transition happens, but it does not leave a lasting mark on baryon number. Did the electroweak transition fail as a mechanism for baryogenesis, or is it pointing toward physics beyond the standard model that alters its character? Many researchers lean toward the second interpretation. If additional fields or interactions modify the Higgs sector, the transition could become first order after all. This is where collider physics enters the story directly. Any new field that couples to the Higgs can change the shape of the Higgs potential at high temperature. That change can strengthen the transition, producing the bubble dynamics needed for baryogenesis. But such fields cannot be added freely. They must respect the precise measurements already made of Higgs properties. The Large Hadron Collider has measured how the Higgs boson decays and how it interacts with other particles. So far, those measurements agree closely with standard model predictions. This agreement places strong limits on how much the Higgs sector can be modified. The electroweak transition can only be strengthened within a narrow corridor of possibilities. This interplay creates a remarkable constraint chain. Early universe cosmology demands a strong departure from equilibrium. Particle physics experiments demand near-standard model behavior at low energies. Any successful scenario must satisfy both. The universe, in effect, must have behaved differently at high temperature, without leaving obvious scars at accessible energies today. Several classes of models attempt to navigate this corridor. Some introduce additional scalar fields that interact with the Higgs. Others extend the symmetry structure of the electroweak sector. In each case, the goal is the same: alter the thermal behavior of the Higgs field enough to make the transition first order while remaining consistent with experimental bounds. There is a historical parallel worth noting. In condensed matter physics, small changes in material composition can radically alter the nature of a phase transition. A pure substance may undergo a smooth transition, while the addition of impurities can produce abrupt behavior. The electroweak transition may be similar. The standard model may represent a finely balanced case sitting just on the smooth side of a boundary. Evidence for or against such extensions does not come only from colliders. Cosmological observations also play a role. A strong first-order electroweak transition would generate a background of gravitational waves. Those waves would propagate through the universe and potentially be detectable by future space-based observatories. This connection between baryogenesis and gravitational waves is one of the most striking developments of recent years. It offers a way to test early universe dynamics that were previously inaccessible. If such a signal were observed, it would provide independent evidence that the electroweak transition was more dramatic than the standard model predicts. At the same time, the absence of such signals would tighten constraints further. It would suggest that if baryogenesis occurred near the electroweak scale, it did so through mechanisms even subtler than current models anticipate. Either way, the electroweak era remains a focal point. Another important ingredient is CP violation. Even if the transition was strong, the amount of CP violation available matters. In many extended models, new sources of CP violation accompany new fields. These sources can enhance the matter-antimatter bias at the bubble walls, but they are also subject to experimental scrutiny. Precision measurements, such as searches for electric dipole moments of particles, place stringent limits on new CP-violating effects. A successful model must generate sufficient CP violation during the electroweak transition, while avoiding detectable signals today. This tension further narrows the space of viable theories. From a broader perspective, the electroweak transition serves as a meeting point between what we know and what we do not. It sits at an energy scale we can study indirectly, yet its early universe role remains uncertain. The standard model predicts a smooth passage. Cosmology demands something more abrupt. This mismatch does not imply that the electroweak transition was irrelevant. Even as a smooth crossover, it reshaped the particle content of the universe. It set the stage for later processes, influenced reaction rates, and determined which symmetries were active. Its failure to generate baryogenesis on its own is itself a piece of information. In that sense, the electroweak era may be acting as a signpost rather than a solution. It tells us where to look and what properties a successful mechanism must have. It also links the origin of matter to experiments that continue today. Each new measurement of the Higgs boson refines our picture of the early universe. As the constraints tighten, attention increasingly shifts to scenarios that operate just beyond the standard model, where new particles briefly influenced the Higgs field and then faded from view. These scenarios do not abandon known physics. They build on it, adjusting only what is necessary to satisfy the conditions laid out earlier. Whether the electroweak transition failed us or quietly points toward new particles remains an open question. What is clear is that it anchors the discussion. It forces cosmology, particle theory, and experiment to confront each other directly. The imbalance does not have to originate where interactions are strongest. It may instead reside in a sector where particles rarely collide, rarely decay, and pass through ordinary matter, almost unnoticed. In that regime, influence appears not through direct signals, but through what fails to appear. Among all known particles, neutrinos occupy this extreme, interacting so weakly that their role can only be inferred indirectly. Part 8. Could neutrinos be the culprit we can't yet catch? If the universe decided the fate of matter and antimatter in a place where almost nothing interacts, then the imbalance we see today may have been set by particles that pass through entire planets without leaving a trace. Neutrinos occupy a strange position in modern physics. They are everywhere, produced in enormous numbers by the sun, by nuclear reactors, by supernovae, and by the earliest moments of the universe itself. Yet they interact so weakly that billions pass through your body every second without notice. For much of the 20th century, they were treated as nearly massless bookkeeping devices added to equations to preserve conservation laws rather than to drive cosmic outcomes. That picture began to change at the end of the 1990s. Experiments studying neutrinos from the atmosphere and from the sun showed that neutrinos oscillate between different types as they travel. This behavior can only occur if neutrinos have mass. The discovery, confirmed by observatories such as Super-Kamiokande and the Sudbury Neutrino Observatory, established that the standard model of particle physics was incomplete. This single fact carries enormous weight for cosmology. Any particle with mass must have acquired it through some mechanism. For neutrinos, the observed masses are extraordinarily small, millions of times lighter than electrons. Explaining such tiny values naturally leads to new physics, often involving particles or interactions that existed only in the early universe. Leptogenesis is built on this opening. Instead of generating a matter of antimatter imbalance directly in the baryon sector, it proposes that the universe first developed an asymmetry among leptons. Neutrinos, as leptons with unusual properties, become the central actors. The imbalance is later converted into a baryon asymmetry through well-established electroweak processes. Within the standard model at high temperatures, certain reactions violate baryon number and lepton number separately while preserving their difference. These processes, often called Sphaleron transitions, were studied in detail during the 1980s. They provide a bridge that allows an excess of leptons to be partially transformed into an excess of baryons. What makes leptogenesis attractive is that it shifts the burden of asymmetry generation to a sector already known to be incomplete. Neutrino masses themselves point beyond the standard model. The same new physics responsible for those masses can also supply the ingredients needed for an early lepton imbalance. One widely studied framework is the seesaw mechanism. In its simplest form, it introduces very heavy neutrino-like particles that existed only at extremely high energies. Their presence allows the ordinary neutrinos we observe today to remain light. The heavier the unseen partners, the lighter the familiar neutrinos become. In the early universe, these heavy neutrinos would have been produced abundantly. As the universe expanded and cooled, they would decay. If those decays violated CP symmetry, they could favor leptons slightly over antileptons. The imbalance need not be large. As earlier parts of this story have shown, even a tiny surplus is decisive. The historical roots of this idea trace back to attempts to understand why neutrino masses are so small. What began as a technical solution to a particle physics puzzle grew into a cosmological mechanism with sweeping consequences. The same equations that explain oscillation data also describe how the early universe might have avoided erasing itself. A key strength of leptogenesis is that it naturally operates at very high temperatures, well before the electroweak transition. This timing helps satisfy the requirement of departure from equilibrium. As the heavy neutrinos fall out of thermal balance and decay, the universe is driven into a state where asymmetries can survive. CP violation in the neutrino sector plays a central role, just as CP violation among quarks was crucial in earlier discussions. Neutrinos' CP violation provides the bias needed to distinguish matter from antimatter. Unlike the quark sector, however, the size of CP violating effects among neutrinos is still largely unknown. Modern experiments are beginning to probe this question. Long baseline neutrino experiments send beams across hundreds of kilometers to detect subtle differences between neutrino and antineutrino behavior. Early results hint at possible CP violation, but uncertainties remain large. For now, the data allow values that could support leptogenesis without confirming them. From a cosmological perspective, this uncertainty is both frustrating and promising. It means leptogenesis is not yet ruled out. At the same time, it places the origin of matter in a sector that is difficult to access experimentally. Neutrinos are elusive by nature, and the heavy particles invoked in seesaw models lie far beyond direct reach. Observational constraints still apply. The lepton asymmetry generated must be consistent with measurements of the cosmic microwave background and with primordial element abundances. Detailed studies show that leptogenesis can satisfy these constraints while producing the observed baryon-to-photon ratio inferred from Planck satellite data. The appeal of leptogenesis also lies in its economy. It does not require radically altering the Higgs sector or introducing large new interactions at accessible energies. It builds on neutrino physics that already demands extension. In that sense, it feels less forced than some alternatives. There is, however, a cost. The relevant dynamics occur at energy scales far higher than those probed by current colliders. Direct tests of heavy neutrino decays are unlikely in the foreseeable future. This makes leptogenesis harder to falsify experimentally, relying instead on indirect evidence and consistency across multiple domains. The situation recalls earlier episodes in physics. The existence of atoms was inferred long before individual atoms could be seen. Their properties were constrained by chemistry, thermodynamics, and kinetic theory. In a similar way, the heavy neutrinos of leptogenesis may leave their imprint through cosmology and low-energy neutrino behavior, even if they remain experimentally inaccessible. Neutrino oscillations themselves offer one such imprint. The pattern of masses and mixing angles observed today reflects the structure of the underlying theory. Certain arrangements are more compatible with successful leptogenesis than others. As measurements improve, entire classes of models may be excluded. Another avenue comes from neutrinoless double beta decay searches. Observation of this rare process would indicate that neutrinos are their own antiparticles. Such a property fits naturally within many leptogenesis frameworks and would provide strong support for the underlying assumptions. Despite these possibilities, the central challenge remains. The particles most responsible for shaping the matter content of the universe may be the ones least willing to reveal themselves. Neutrinos carry information across cosmic distances, yet interact so weakly that extracting that information requires extraordinary care. From the standpoint of early universe physics, this weakness becomes a feature rather than a flaw. Weak interactions allow asymmetries to persist, Strongly interacting sectors tend to equilibrate quickly, washing out differences. Neutrinos, by barely participating, can preserve imbalances long enough for them to be converted and frozen in. In this light, the neutrino sector appears almost purpose-built for baryogenesis. It sits at the intersection of known deficiencies in the standard model and the stringent requirements imposed by cosmology. It offers a mechanism that is minimal in spirit, yet profound in consequence. Still, leptogenesis does not stand alone. It competes with other scenarios, each with its own strengths and weaknesses. What distinguishes it is not certainty, but plausibility grounded in existing anomalies. The masses of neutrinos are not optional. They are measured facts. Any explanation of the early universe must accommodate them. As experiments refine our understanding of neutrino properties, the space of viable leptogenesis models will shrink. Some possibilities will be eliminated. Others may gain support. In either case, the role of neutrinos in cosmic history will become clearer. If leptogenesis is correct, then the universe's survival depended on particles that rarely interact, whose influence is subtle and indirect. The balance between matter and antimatter would have been tipped quietly long before protons and neutrons formed in a sector almost invisible to us today. And yet even this elegant picture must confront the discipline of precision. The same CP violation needed to generate a lepton asymmetry cannot contradict sensitive laboratory measurements. As those measurements improve, they will test whether neutrinos truly carried the decisive imbalance, or whether another mechanism must be sought. This tension is resolved not by speculation, but by measurement. If additional sources of CP violation exist at the required scale, they should leave subtle but detectable imprints. For decades, experiments searching for electric dipole moments have been built precisely for this purpose, pushing sensitivity to levels where even the smallest asymmetries would stand out against the background. The absence of such signals now places some of the strongest constraints on how baryogenesis could have occurred. Part 9. Why do electric dipole moment searches threaten entire baryogenesis ideas? If the universe required new sources of CP violation to survive its first moments, then there is a stark possibility that the same imbalance should already have revealed itself in the quietest laboratories on Earth. An electric dipole moment, often abbreviated as EDM in the literature, is a simple idea with severe consequences. For a particle such as a neutron or an electron, it describes a separation between positive and negative electric charge along its spin direction. In a perfectly symmetric world, this separation would be exactly zero. The charge would be distributed evenly. Any non-zero value would signal a violation of time reversal symmetry, and through well-tested principles CP symmetry as well. This connection makes EDMs extraordinarily powerful. Unlike high-energy collider experiments, which attempt to create new particles directly, EDM searches look for minute distortions in familiar particles. They do not require extreme energies. They require patience, stability, and precision at levels that push experimental control to its limits. The relevance to baryogenesis becomes clear once the role of CP violation is recalled. Every viable mechanism for generating a matter-antimatter imbalance relies on CP violation beyond what the standard model comfortably provides. If new sources of CP violation exist, they should not remain entirely hidden. Even if they operate most strongly in the early universe, they generally leave faint echoes at low energies. Electric dipole moments are one such echo. Many extensions of the standard model predict EDMs that are larger than the tiny values produced by known physics. In fact, the standard model contribution to the neutron or electron EDM is so small that it lies far below current experimental sensitivity. This makes EDM experiments a clean window onto new physics. The history of EDM searches stretches back decades. Early efforts focused on the neutron, motivated by the understanding that quark-level CP violation could induce a measurable effect. As experimental techniques improved, attention expanded to atoms and molecules, where internal electric fields can amplify sensitivity to electron EDMs. In recent years, experiments using ultra-cold neutrons, trapped atoms, and polar molecules have achieved extraordinary precision. They can detect energy shifts corresponding to charge separations, smaller than the diameter of a proton by many orders of magnitude. Yet despite this sensitivity, no definitive EDM has been observed. This absence is not a neutral result. It is an active constraint. It tells us that any new CP-violating physics must be either extremely weak, very heavy, or arranged in such a way that its low-energy effects cancel out. For baryogenesis models, this creates a narrow passage. On one side of the passage lies cosmology. To generate the observed baryon asymmetry, CP violation must be strong enough under early universe conditions to bias reactions by roughly 1 part in a billion. On the other side lies precision experiment. The same CP violation must be subtle enough to evade detection in EDM searches. Threading this gap is not impossible, but it is restrictive. Many otherwise attractive models fail this test. They predict EDMs that should already have been seen. When experiments report null results, entire classes of baryogenesis scenarios are quietly removed from consideration. This is why tabletop experiments can act as a cosmic veto. They do not recreate the early universe. They do something more unforgiving. They check whether the required asymmetries are consistent with the symmetries still observed today. A useful way to think about this is through scale separation. Baryogenesis often occurs at very high energies, perhaps near those associated with grand unification or heavy neutrino masses. EDMs, by contrast, probe physics at everyday energies. If a new interaction violates CP symmetry, its effects typically persist across scales, unless suppressed by symmetry or structure. Some models achieve suppression naturally. For example, CP violation may reside primarily in sectors that couple very weakly to ordinary matter. Alternatively, different contributions to the EDM may cancel each other. These possibilities keep certain baryogenesis mechanisms viable despite experimental bounds. However, such arrangements come at a cost. They reduce predictability. They introduce additional parameters that must be tuned carefully. The more tuning required, the less robust the explanation appears. Precision experiments force theorists to confront this trade-off directly. There is also a historical lesson here. In the 1960s, CP violation was discovered in neutral kaon decays. At the time, it seemed like a small curiosity. Only later did its cosmological importance become clear. EDM searches follow a similar pattern, but in reverse. They search for a signal whose absence is already shaping theory. The current limits on the electron EDM, derived from molecular experiments, are particularly severe. They imply that any new CP-violating physics affecting electrons must be suppressed to an extraordinary degree. This has direct implications for electroweak baryogenesis models that rely on new phases in the Higgs sector. Neutron EDM limits provide complementary information. They constrain CP violation in the strong and electroweak interactions of quarks. Together, electron and neutron EDM searches carve out a detailed map of what new physics can and cannot do. From a cosmological standpoint, this map is invaluable. It allows researchers to discard ideas not because they fail in principle, but because they conflict with reality at measurable levels. The early universe becomes a testing ground constrained by laboratory evidence. There is an irony in this situation. The mechanisms that may have determined the fate of all matter are being judged by experiments conducted in small rooms using fields and traps and lasers isolated from cosmic drama. Yet the logic is sound. Physics does not forget its symmetries. It is also worth noting that EDM searches continue to improve. Each new generation of experiments tightens the bounds by orders of magnitude. What is allowed today may be excluded tomorrow. This progressive narrowing makes the future of baryogenesis research sharply defined. Some scenarios survive precisely because they predict EDMs just below current sensitivity. In these cases, upcoming experiments could deliver decisive results. A single non-zero measurement would immediately identify new CP-violating physics and transform the discussion. If such a signal were found, it would not merely confirm a particle property. It would illuminate the mechanism that allowed matter to dominate antimatter. It would link the quiet asymmetry of a particle to the existence of stars and galaxies. Until then, the absence of EDMs remains a powerful statement. It does not deny baryogenesis. It disciplines it. It demands that explanations be subtle, consistent, and compatible with everything already measured. This discipline has reshaped the field. Rather than proposing mechanisms freely, theorists now work backward from experimental limits. They ask not only what could generate an asymmetry, but what could do so without leaving forbidden traces. In this sense, EDM experiments serve as guardians of coherence. They ensure that cosmological speculation remains anchored to laboratory fact. They prevent the early universe from becoming a playground unconstrained by present evidence. As a result, the matter-antimatter problem is no longer addressed in isolation. It is entangled with precision physics at the smallest scales. Each null result tightens the narrative, forcing the imbalance to hide in narrower corners of theory. Two facts now coexist without resolution. Sources of CP violation beyond the standard model appear necessary for matter to dominate. Yet experiments sensitive enough to detect even minute violations have found nothing so far. Both results rest on solid ground, and neither can be dismissed. Holding them together forces a different kind of conclusion. If matter endured through mechanisms that are physically real yet difficult to observe, then the issue is no longer whether dominance occurred, but what its continued presence implies about the reach and the limits of the theories we rely on. Part 10. If the universe shouldn't have survived, what does that say about our theories? Not our feelings. When the numbers insist that matter and antimatter were born almost perfectly balanced, yet everything we observe proves that balance was broken. The question is no longer whether the universe survived by chance, but what is absent from the Bohr equations we rely on. By the time modern cosmology reaches this point, the ground beneath the discussion is firm. The matter-antimatter asymmetry is not inferred from a single observation or a fragile assumption. It is supported independently by measurements of the cosmic microwave background and by the abundances of light elements formed during Big Bang nucleosynthesis. These two epochs are separated by hundreds of thousands of years, governed by different physics and measured with different instruments. Yet they agree on the same conclusion. The Planck satellite mapped tiny temperature fluctuations in the cosmic microwave background with extraordinary precision. From those fluctuations, cosmologists extract the density of baryonic matter today. Independently, calculations of primordial hydrogen, helium, and lithium abundances depend sensitively on how many baryons were present when nuclear reactions first froze out. Observations of ancient gas clouds and stellar atmospheres confirm those predictions within narrow margins. The agreement between these methods leaves little room for doubt. The baryon-to-photon ratio is small, roughly 6 parts in 10 billion, but it is real. It did not evolve arbitrarily. It was set early and preserved. Any explanation of cosmic history must reproduce this number. Against this backdrop, the standard model of particle physics appears both successful and incomplete. It describes known particles and interactions with remarkable accuracy. It predicts outcomes tested at accelerators, in nuclear reactions, and in astrophysical environments. Yet when applied to the origin of the baryon asymmetry, it falls short in most conventional analyses. This shortfall is not subtle. Calculations that include known CP violation, known baryon number violating processes, and the measured properties of the Higgs field consistently yield asymmetries far smaller than required. The universe, according to these equations, should have evolved into a state dominated by radiation with matter and antimatter annihilating almost completely. That did not happen. Galaxies formed, stars ignited, chemistry unfolded. The discrepancy is not emotional or philosophical. It is quantitative. It is a mismatch between predicted and observed outcomes. Over the course of this series, several candidate resolutions have been examined. Electroweak baryogenesis explores whether the Higgs field could have provided the necessary conditions. Leptogenesis shifts the imbalance to the neutrino sector, leveraging physics already known to extend beyond the standard model. Precision experiments, particularly searches for electric dipole moments, impose strict limits on how new sources of CP violation can behave. Together, these ideas outline a constrained landscape. The required ingredients are known in abstract, baryon number violation, CP violation beyond the standard model, and departure from equilibrium must all be present. What remains uncertain is how nature arranged them without contradicting existing measurements. This uncertainty does not imply disorder. On the contrary, it defines a research program. Each missing ingredient corresponds to a testable target. New CP violation motivates precision experiments. New fields motivate collider searches and gravitational wave observatories. High-energy dynamics motivate cosmological probes of the early universe. In this sense, the matter-antimatter problem functions as a map rather than a dead end. It points towards specific directions where established theory is likely incomplete. It also explains why so much attention is focused on phenomena that seem marginal at first glance, such as tiny symmetry violations or rare decays. There is historical precedent for this pattern. The perihelion precession of Mercury did not overthrow Newtonian mechanics overnight. It revealed a small discrepancy that persisted until a deeper theory, general relativity, accounted for it naturally. The matter-antimatter asymmetry may play a similar role. The quote often attributed to Steven Weinberg captures a related tension. The more the universe seems comprehensible, the more it also seems pointless. In context, this remark reflects discomfort, not despair. It underscores that understanding laws does not automatically explain initial conditions or specific outcomes. Clean equations can still conceal missing mechanisms. What distinguishes the present problem is that the missing mechanism is not abstract. It has measurable consequences. It must leave traces consistent with what we already observe. The universe did not simply choose matter. It followed rules that we are still uncovering. It is also worth emphasizing what this problem does not require. It does not require rewriting all of physics. The standard model remains extraordinarily successful within its domain. General relativity continues to describe cosmic expansion and structure formation accurately. The challenge lies at their intersection in regimes, where known frameworks overlap but do not fully constrain outcomes. Future progress will likely come from multiple directions at once. Improved measurements of neutrino properties may clarify whether leptogenesis is viable. Next-generation electric dipole moment experiments may reveal or further restrict new CP-violating physics. Gravitational wave observatories may detect signals from early universe phase transitions. Each of these advances would not merely add detail, they would remove ambiguity. They would narrow the range of possible histories the universe could have followed. Until then, the survival of matter remains a statement about our theories, rather than about improbability. The universe did not defy its equations. It obeyed a set of rules that we have not yet fully reconstructed. That distinction matters. It keeps the discussion grounded. It frames the mystery as an invitation to refine models, not to abandon them. The absence of a complete explanation is not a failure of science. It is a sign that the boundary of understanding has been reached and clearly marked. In that light, the antimatter mystery stands as one of the most disciplined, unsolved problems in cosmology. It is constrained by data, guided by theory, and connected directly to experiments underway. Few questions about the early universe can claim such a position. What remains is neither certainty nor closure, but a structure that holds together what has been measured so far. The asymmetry is real. It appeared early, and the mechanisms available within the standard model do not seem sufficient on their own. Taken together, these facts narrow the space of explanation, even as they leave its boundaries open. Thank you for spending this time here, following the evidence from the earliest fractions of a second to the edges of present theory. Your presence and attention are deeply valued. Wherever you are listening, and whatever hour has brought you this far, may the rest of your night continue undisturbed. Good night.